Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solve the problem number 11. Let's consider this network consisting of 5 resistors labeled R1 through R5, as well as 2 independent voltage sources V1 and V2 and 1 independent current source IS. The question now is to calculate the value of Vx using Thevenin's theorem. Vx is the voltage across the resistor R3. Let's move on to the solution. By applying the Thevenin's theorem between terminals A and B, we can replace this circuit with the voltage source in series with the resistor, which will be denoted as VTH and RTH. In our example, RTH is connected in series with the R3, which plays the role of the load. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuit, which means the voltage sources will be replaced by a short circuit and the current source will be replaced by an open circuit. The Thevenin's resistance represents the equivalent resistance between terminals A and B when R3 is disconnected. That means RTH is equal to the parallel combination of R1 and R2 connected in series with the parallel combination of R4 and R5. Therefore, RTH can be calculated using the following formula. And if we replace the resistors with their numerical values, we obtain RTH is equal to 32 ohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage between terminals A and B when R3 is disconnected. The voltage VTH is equal to VOC, the open circuit voltage. And in order to find the open circuit voltage VOC, I will apply the nodal analysis method. And I will consider I1 is the current through the resistor R1, I2 is the current through the resistor R2, I3 is the current through the resistor R4, and I4 is the current through the resistor R5. By applying Kirchhoff's current law at node A, we can write I1 minus I2 is equal to 0. The current flow in this direction is equal to 0 because we have an open circuit. By applying now Kirchhoff's current law at node B, we can write IS plus I4 minus I3 is equal to 0. According to Ohm's law, I1 is equal to V1 minus VA over R1, I2 is equal to VA over R2, I3 is equal to VB over R4, and I4 is equal to V2 minus VB over R5, where VA and VB are respectively the node voltage at node A and B. Now by substituting A and B in 1, we can write V2 minus VA over R1 minus VA over R2 is equal to 0. And if we replace the voltage and the resistors with their numerical values and we continue simplifying this equation, we obtain 180 minus 3 times VA is equal to 0. Now by substituting C and D in 2, we can write IS plus V2 minus VB over R5 minus VB over R4 is equal to 0. And if we replace the current the voltage and the resistors with their numerical values, and we continue simplifying this equation, we obtain 480 minus 5 VB times VB is equal to 0. From equation 3, we can calculate VA is equal to 180 over 3 is equal to 60 volt. And from equation 4, we can calculate it VB is equal to 480 over 5 is equal to 96 volt. VTH is equal to VOC is equal to VA minus VB is equal to 60 minus 96 is equal to negative 36 volt. In order to calculate the voltage Vx, I'm going to use the voltage division rule. That means Vx is equal to R3 over R3 plus RTH times VTH. And if we replace R3, RTH and VTH with their numerical values, we obtain Vx is equal to negative 8.57 volt. After completing the calculation, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in SPICE simulator. This is the original circuit, and this is the equivalent Thevenin circuit. I connect here a voltmeter in order to measure Vx in the original circuit, and here I connect a voltmeter in order to measure Vx in the equivalent circuit. Let's move on to analysis. They say analysis, calculate nodal voltages. We can see here that Vx is equal to negative 8.57 volt in the original circuit, and Vx is equal to negative 8.57 volt in the equivalent circuit. From the simulation, it becomes clear that the voltage Vx is similar when using both the original circuit and the Thevenin equivalent. This similarity validates the correctness of our calculation. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video, and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Thevenin's theorem. Take care and bye-bye.